In this section, we will consider the concept of center of mass. The center of mass of an object is defined by the following two sets of equations for their components. The center of mass is a vector, and it is a vector that represents, in essence, the average location of an object. If you have an object that's a point, the location is at a specific point. But when you have an object, let's say something like a bar here, and the bar has some finite length, then where do you mean the location of the bar? Are you meaning this point, this point, this point, or maybe that point? And in particular, which point, if any, on the bar behaves according to Newton's laws? Well, it turns out you could represent a bar as a set of points, atoms, if you would. And if you solved all the forces around those atoms, you could actually describe completely the object as it moves through. There's actually a group at Tarleton called a particle modeling group that's run by Dr. Bryant Wyatt, who uses supercomputing capabilities to try to do this. But what we want to do is to try to handle a problem like that without using large-scale computing, and to be able to handle it with pen and paper. And it turns out we can do that. The place that represents in space the object and obeys Newton's law is this very special place called the center of mass. Now, these formulas for the two components of the vector of the center of mass, which we'll eventually be able to put into our equation to make a vector like this, look very complicated, but in fact they're not. What they really are is simply find the average x location and find the average y location. And so the best way to do this is to go and understand this through examples. And I talk about this a little bit in the notes, which I'll leave for you to read. But what it is that the mass looks like the number of people or number of kids in a class scoring a particular score. So that's the number of kids, and this is the score they make. Maybe that happens to be 100. So if 4 kids made 100, the mass would be 4, the score would be 100. And you'd take 4 times 100, and what that would do is determine the number of points on those papers. And you would do this for every possible score. And at the end, you would divide by the number of students, and that would find the class average. This x-coordinate for the center mass is like the average class score. So let me show you, using this formula, how this works. Find the center mass for the following system. Somewhere here, there's a location x equals 0. And we have a set of masses here. To find the center mass, we take the first mass, 2 kilograms, and multiply by its score, 20 centimeters. All right, 20 centimeters. Then we take the next score, 1 kilogram, and multiply its value, 40 centimeters. The next score, 2 kilograms, 60 centimeters. 5 kilograms times 80 centimeters. And last but not least, we have 8 kilograms times 100 centimeters. And I'm unfortunately kind of off the screen. And then you got to divide by all of the students. 2, 1, 2, 5, 8. So 2 plus 1, that's 3 kilograms, plus 2 kilograms is 5, plus 5 kilograms is 10, plus 8 is 18 kilograms. So you take that, and we take our calculator, of course, and we calculate what that value is. So 2 times 20, that's 40, plus 40 is 80. Plus 120, plus 5 times 80, plus 8 times 100. And you get 1400, and then I divide that by 18, and I come up that the center mass is approximately 77.8 centimeters. Or, if you prefer in meters, 0.778 meters. Now, if you look at this problem and hopefully compare it to the problem with the class average right above it, you see that I took exactly the same sort of thing. The scores were like the locations. These were like in centimeters, and the number of students were like the kilogram masses, and the class average was 77.8. The x-coordinate here was 77.8. Try to see if you can't get a picture for this where you see how the center mass represents the class average. Now, something else that it does, it tells us that if we were trying to balance this, that this is a teeter-totter, that if we put something at 77.8, which is somewhere right about there, that we could balance this. There's some big masses over here, but the light masses are further away, and because they're further back, they can offset these bigger masses that are closer, and this will make it balanced. So another way to look at the center mass, it's the location here for balancing this object, like on a playground. Let's do another example, this one being a two-dimensional example. So this time they're not aligned on a line, they're lying in an XY plane, and so we'll have to compute both the X value of the center mass and the Y. To do the X, I like to always label my particles, so this is particle 1, 2, 3, 4, 5. That just helps make sure I get them all right. I got 3 kilograms. That's located at an X value of 1, 2, 3, 4, so that's at 4 meters. I have 1 kilogram. That's located at 1, 2 meters. I have 1 kilogram. That's located at a distance 1 meter. I have 2 kilograms, but it's located on the y-axis, which is at a distance of 0. So that's like a person who scores 0. He doesn't add to the points. And I have this one, which is 5 kilograms, and it's at a location of minus 2 meters. And then I have to divide by the total mass. 3, 4, 5, 7, 9. 9 kilograms. That gives me a center of mass. Let's see. 3 times 4 is 12. Plus 2 is 14. Plus 1 is 15. Did I get that right? Oh, this was not 2. This was wrong. This was a 2 kilogram mass. I read my 5 and not the 2. Alright, so 12 plus 2 is 14. Plus 1 is 15. Minus 4 is 11. Kilograms meters over 9 kilograms. That's 1 and 2 ninths. 2 ninths is 0.222. So that's the X coordinate. So that's like saying that what I need to do to balance this is somewhere along here. If I could draw a line, not a good line, but somewhere along that area. Now we need to find the Y. Do the same thing, 3 kilograms, but this time we look at their Y score. So you can think of this as the score in physics maybe, and this is your score in your math class. So that was the physics average. Now we want to look at the math average. I got minus 2. This one is at 0 on the Y because it's on the x-axis, so it doesn't count. This one up here, I got 1 kilogram. Its Y value is 1, 2 meters. The next one is 2 kilograms. Its Y value is 1, 2, 3, 4 meters. And the last one is 2 kilograms. And its Y value is 1 meter. And again, the total mass doesn't change. It's 9 kilograms. So we'll go and compute this one. So let's see, I have 3 times minus 2 is minus 6, plus 2 is minus 4, plus 8 is 4, plus 2 would be 8. Assuming I've got that right. Minus 6 plus 2 would be minus 4, plus 8 is 4, plus 2 would be 6. So that would be 6 kilogram meters over 9 kilograms, 0.667 meters. So the center of mass is a vector whose location is 1.22 meters I hat plus 0.667 meters j hat. And if we go up here, one of the nice things we can do is we'll draw us a line over here, a point somewhere like right along here. And so right there, that's the center mass. That's the place that would balance. Now, one of the things to note is there's no mass at the center mass. Just like no one in the class may have scored the class average. You can have a student who makes 100 and another student who made 0. If there's only 2 students in the class average is 50, but neither student made a 50. It represents the object as a whole. It does not mean that any matter specifically has that value. And this is some things that are kind of important to put. Center mass will often reside at a location in which no particle exists. And sometimes an object, if it's homogeneous, that is, it's made of uniform material, you might be able to determine the center mass without doing any calculations. For instance, here's a center mass for a toroid. A toroid is the scientific term for donuts. I personally like mine glazed. So I like glazed toroids. Right there in the middle. At least if I'd done it in the middle. I guess I didn't quite. Let's see if I can get a little better. All right. There's the center mass. And I didn't need to do any advanced calculation to do that. So the center mass can often be found just by looking at things. And we'll find this useful when dealing with more advanced problems. All right, that handles it for this video. We'll come back and look at how to analyze more complicated things like the human body by applying the center mass in the next video.